In the last class we had talked about self-attention. Okay, that is one of the very key components of transformer, and now what I will do is I will try to make a transformer. Okay, now the problem is, so we will do it the way it is done in the blog post by JLMR, something that I have already told to you, okay, so that you can go and read that blog as many times as you want, and that blog is referred everywhere. Whichever course you go on transformers, that blog is very well referred. So date is 28/02/2024. Now, so we are going to talk about transformers now. And we will simply just try to draw. Okay. So, or see, I will try to do it the way it is done in this blog, so that when you read the blog things are much clearer. Now, at a high level, what is happening? So, at a high level you give input to the transformer. So, for example, the original transformer paper, attention is all you need, right? It solved which problem? See, original transformer paper was written for machine translation only, okay, and later papers like BERT, they said that these architectures are actually very much generalizable. Okay. So, one thing could be, so this transformer is our black box here. So, right now we are doing transformers in the context of translation only, the way it was done. So, you give input in language 1 and you get output in, so basically in this case some target language, and this is your source language. So this is what at a very high level transformer does, right? But we are going to look at every detail of it. So again, I have said this many times, I am going to refer to the blog post of JLMR. Now, so transformers, they are actually not, so if this were just deep learning architecture, how would this black box look like? So, do you think a normal feed forward neural network is a good candidate here? You think a normal feed forward neural network is a good candidate here, yes or no? Why not? Feed forward neural networks we had ruled out long ago. We had said that they can't take care of sequence. So you could have RNNs here. Particularly in the RNNs you could have encoder and decoder architecture. I mean, of course, when I say RNNs I actually mean LSTMs. Okay. So you could have encoder decoder architecture. Then next we said encoder decoder architecture of LSTMs plus what? Something that we did a couple of lectures ago, attention mechanism. Okay. So that actually improves that encoder decoder a lot. Now transformer paper comes and say you can get rid of recurrence altogether. See, look at this story the way it is coming. Normal feed forward networks are not okay, you must use RNNs. RNNs suffer from vanishing gradients, you must use LSTMs. LSTMs In LSTMs you will use encoder decoder architecture. In that encoder decoder architecture, if you start using attention, then things are much improved. Then what next? This paper. This paper comes and says attention is all you need, recurrence is, so what is hidden here is recurrence is not necessary. Make sense? Okay. So now, how does this thing look like? So the way it was done, so I won't be writing this whole thing, and I'll just write input output from now on. So transformers are basically, so this whole transformer is nothing but encoder. So even transformer is encoder decoder architecture, but it does not use LSTMs, it does not use RNNs. Okay, so again you have a input and output. Now this, the next level of detail is this. So this was just one black box. Now we are saying this black box itself consists of two black boxes. So what could next be? And yes, you have, so wherever you have encoder decoder architecture, you will have something being passed from encoder to decoder. That is by definition of encoder decoder, because somebody will encode something and then a decoder is supposed to decode. Okay, so whatever encoder has encoded, that has to be passed to decoder. Okay, what more now? Now if you see here, so this whole thing now I'll be just drawing. So this is the transformer block now, and you have input, and then you have encoder, you do 6 such things. Okay, so you have 6 such encoders. Okay, that one encoder is now 6. Okay, now what you do is you pass the, so what will we do here? We will have decoders here, decoder, how many do you expect? How many do you expect? Right, so the best guess would be 6. Does anything stop me from having 7 there, or 7 here and 6 there, or vice, or whatever? Nobody stops you from doing whatever, right? That is how deep learning has evolved. So you can do whatever, provided you can write a code, train on your data set, and show that It works. What does it mean? It works. It generalizes well on unseen data. You can throw away your machine learning algorithm, whatever it is, if it does not generalize well. Okay? If you do 50 courses on machine learning, all will teach you this one thing. You design machine learning algorithms to generalize well. Okay? So this is a transformer block case. Okay? And we, of course, so this was the input here now. We are doing that same thing that we were doing with RNNs, that I mean in terms of drawing. So and then you get output here. What is still missing? Right. So what encoder passes to decoders. Okay. Now, what can happen here? How do we pass from encoder to decoder? So who should pass to whom? And my question is, let's say whatever you say, can I call it wrong? Which one is wrong? Sorry?
Anything that does not generalize on data is wrong.
No, that's not wrong. You just have to throw that thing away because it does not generalize well. But nothing is wrong in this area. And that is the reason I can't ask you very tough questions in exams. Right? Because whatever you write, you can always argue this makes sense. Okay? So to be able to fix something, this should be the answer, it's a very difficult question to frame. And if I am able to frame it, then that question will most likely be trivial to you. So, right. So the way see, you can do all sorts of things. There are 6 elements here, 6 elements here, so you can think of it as a bipartite. Everybody knows bipartite graph. What is it? Right? So all of 6 you can send, you can easily have this guy sending here, this guy sending here, 3, 4, 5, there was one more here. Okay? Nobody stops you from doing this, and this is all perfect and okay. Right? Any combination that you want to do, 3 of them passing 3 of them here, 3 of them passing 3 of them here, mathematically they are not wrong, right? But many of them will not make sense intuitively. So what you actually do, in this case, in the case of transformers paper, this is what happens. Okay, so this outermost, the latest, the one in the last, right? This encoder, whatever it has encoded, pass it to all the decoders. Now, this is different from the way we were doing it in LSTMs. What did we do in LSTMs? Whatever was computed by encoder, that one representation, 1H, 1A, whatever we call them, right? That was passed to the input of the decoder, right? So complete output, the final output of encoder was passed to the decoder. Okay? In this case, you are passing it to every decoder unit. Okay? And now, once this paper was published, tell me what will later papers do? So they will try to change this, change that, and show that this transformer works better than the original one, okay, and so on. So that has also happened a lot. And all GPTs, BERT, they are all just transformer based architectures. So this is straightforward, I think. Make sense? And I think I have not made any mistake either. Okay, important thing here to note is all encoders, even though they are same in size, but they don't share weights. Okay, maybe you may write this down and we'll later fix. So what does it mean to say they don't share weights? What does it mean to say weights are not shared? Okay, in what sense? They are of the same size. So what is the difference? See, if I give you a normal feed forward network, 100 input, then the next hidden layer has 50, the next hidden layer has 50, first hidden layer has 50 neurons, second hidden layer has 50 neurons, third hidden layer has 50 neurons, fourth hidden layer also has 50 neurons, and the last one has just one. So you are doing binary classification. Tell me, what will be the parameter matrix W2? 50 cross 50. What will be the parameter matrix W3? 50 cross 50. But does it mean they are same? So what is the difference? Their dimensions are same, but what is different? The parameters that you learn are different. So just because two matrices are of the same dimension does not mean that they are same, right? So the moment you say these two parameters are different, they have nothing to do with each other, matrices are actually different, they just happen to have the same size. Okay, so all the parameters here are different, they are not shared. What should we do next? What is the next logical step to do? Let's talk about just one piece. Okay, because all 6 are same, so let's talk about one encoder. And since we are calling it encoder and we are calling this decoder, these two guys should have some differences too. Okay.
Sir,
Yes.
वो लास्ट वाले encoder पे सबसे ज़्यादा डिफरेंस है, तो इसमें हम वो attention वाला भी रखेंगे। मतलब सबसे पहले तो इसकी लेंथ कितनी हो सकती है, जैसे STMs में अगर हंड्रेड्स में हो सकती है तो इसमें कितनी, तो सीक्वेंस को कैसे वो करेगा?
So I postpone this question. Okay. So inputs you are all feeding here. We will come to that part. Okay. So now let us talk about just one encoder. So this is one encoder now. Okay, and what it has is something that you already know. So this is your self attention, and this is your what is NN? Neural network, right? So self attention feed forward neural network. What is this thing? One encoder. Okay. So of course this will pass here, and then this guy passes to the next one, and of course it has to receive inputs. Okay. What is feed forward neural network? Good old neural networks, the very first neural networks that we had done. What is self attention? We talked about this in the last class. Okay. Okay, so maybe I'll give you some time to write this down, and by that time Okay, now we come to what she was asking. So how does this, so we have broken it down to, quite a good level now. How does this guy take input? So this is my self attention, let's say. Okay, so this is my self attention layer. And I am not calling it layer. So I mean self attention layer, but I am just leaving that word. So how will this take input? Now this is something we did in last class. What was that? Yes. How will this guy receive inputs? This we did in last class. So what this thing looks like is, this is this one, right? What were the inputs taken here? So in this case you had Tx, okay. Now Tx inputs all fed to that self attention, and then you compute whatever comes next, whatever. So this is that self attention thing that I am talking about there, okay. So we go back there. Right. So how many inputs? This is your x1. This is your x2. Okay. And finally this is your x512. Okay. And let me just make sure this is 512. Okay, I don't see it anywhere, but from what I remember, this is 512, and this is 512 for GPT-1 as well. So I am actually, with these numbers I am confused between GPT-1 and BERT and transformers. So I may get these numbers wrong, okay, but that does not matter. So x12, 512. Now how will each x1 be what is x1? So if now we were talking about small sentences, what was our example? Ila montarte, okay. So in that case, il a montarte, so il a tarte, okay. Now 4 words. Now you can input 512 tokens, and right now for the time being we'll fix this thing later, but right now to us each token is a word. So what we are saying is my text is separated by spaces. That's an easier thing to do, right? No, so these are 512 words, but how do you do words as input to neural networks? Their embeddings. Okay. So here what you are actually passing is E of x1. Now E of, are we using E somewhere else too? So E is basically word embedding. So how should I write? So maybe word embedding of x, because we will never use this thing after. So word embedding of x1, x2, x3 and so on. What will self attention do? Whatever it does for the time being, it will pass for every. So how many outputs will be there? 5, 1, 2. Okay. So whatever self attention does, it does to all these vectors and passes it up. Now it is received by a feed forward neural network. Okay. So this one was 300 dimensional. What happens here? So this whole thing is, if you see here, we are just trying to talk about this block separately here. So here we just do them as, you know, black boxes. Now we are trying to see what is inside even them. Right. So what are the dimensions of word embedding x1? This we have been taking standard 300 cross 1 and I have said it n number of times. This doesn't have to be 300 cross 1. It can be whatever you want it to be. Next. Yes. Token?
Word embedding?
No. Token, see, token you call, right now you are calling a word as a token. Okay. Later we will fix it because they actually bring it to the subword level. So when we'll talk about BERT, we'll actually fix it very concretely. Right now we are saying I'm given a long corpus and I take, let's say, first, so this has to be of course 512 continuous tokens in any document. Okay, can't be random. It has to be 512 continuous tokens. And for us right now, tokens means words. So basically it's an easy program to write. Wherever you see space, so between two spaces you have one token right now. Okay. Now what will happen here? We have talked about this in the last class. So what happens here? So you compute. So now let us talk a little bit more about what we did in the last class. So what happens here? So just talk about what happens here now. You give x1, what is your output? One more thing. So before I go further, all these things, right? So the output here So let me just try to guess you. Output here will be 512 dimensions. This, so output of my first encoder, they look like this. There are 512 output of size 512 each. So how do I fix the parameter matrices and everything? What is x1? So word embedding of size 300 and word embeddings are now gone. Now, right? So what comes next? So how do I make these guys 512 each? First talk about query key values. So yes, first talk about query key values. In fact, I think it's a good idea to say that this is what we are talking about. Yes. So you had three matrices here. What were they? Query, key and value. So if I do, how will I get my query vector for 1? Q x1, and then what will I get? What will I get next? K1 will be capital K x1. Now, since we use W, okay, for weight matrices, what is also done? So in many literature you will find it to be WQ, WK, so that it is evident you are talking about parameter matrices. And similarly, what was the last thing? V1. So V1 is going to be WVX1. Do WQ, WK, WV, do they have to be of the same dimensions? What are the dimensions of X1? 300 cross 1. What are the dimensions of Q1 we are saying? Last time what did we say? We want this Q1 to be 64 cross 1. If you want it to be 128 cross 1, anything wrong with that? No. Okay. So all these guys are 64 cross 1. Okay. Now what was x1? 300 cross 1. So this is 300 cross 1. And now again this was our choice. So this fixes W to be 64 cross 300. Is that right? 64 cross 300, right? Okay. So you get the dimensions of this. So if you see here, what is the output here? V1. So again I need to do something here. K1 and Q1. But this is just self-attention. It is not the output of self-attention. What is the output of self-attention? So how do you compute the output? So this output is not this one. What is the output, actual output? So I think I should not be doing this. Let us improve this. Where should I draw this? Let me draw this just inside. So you have computed Q1, V1, K1. So I mean, you know, these kind of things I keep on doing. There it was subscript, here it is superscript, but you understand. Okay. So what is the output? Output are not these three vectors. What is the output of this unit? Just one. Can you just compute it by just this block? No. Self attention means Q1 dotted with K1 dot, and then you have to take dot product with all. So you see there are and QKV. Which QKVs are they? Q2, K2, V2. Q 512, K 512, V 512. Okay. What will be the output of this that I feed to my neural network there? This is easy. I mean, this is what we did in last class. So alpha 1 times V1 plus alpha 2 times V2. So how many terms here total? 512. When you sum them up, it will be a vector of size. What will be the size of my final output here? What are the dimensions of alpha 1? Alpha 1 is a scalar. What are the dimensions of something that it gets multiplied with? 64 cross 1. So scalar cross 64 cross 1 plus scalar cross 64 cross 1. How many times you do this operation? 512 times. Resultant is a 64 cross 1 vector. Make sense? So this is 64 cross 1. Now, is this 64 cross 1? All the outputs here, be it this one, be it this one, they are 512 dimensional. And right now this is just 64. So you want to say I should not be having 64, instead I should have 512, right? Everybody agrees? So we should not have 64, we should have 512. But this is not what the authors have done. They have done something different. Okay? They have something different called multi-head attention. Now what might this mean? Everybody knows self-attention? Now we are talking about multi-head attention. What may multi-head attention mean? So let me specifically write, this guy is 64 cross 1, this guy is yes. So then I should, so maybe now people will understand by now that we are talking about this one. Yes. So this is 64 cross 1. How do I make it 8? One option was you make WQ of size 512 cross the dimension of your word embeddings. Okay. What they have done is, so let us call this for one head. So this you are doing for one head. You have how many heads you want? 8 such heads. If you have 8 such heads, how many WQs, WKs, WVs you will have? You will have as many WQs, WKs, WVs, as many heads you want. So how many heads you want? Now tell me, what was this attention doing? Remember that the animal could not cross the street because it was too tired. The animal could not cross the street because it was too tired. It refers to the animal. But will you necessarily have this kind of sentences where one pronoun refers to other and there can't be any other thing referring to something else in a sentence to learn? You can have much more complicated relationships. Okay. So authors say this particular 64 cross 1 will take care of one such relationship. You have another attention head that might take care of relationship between other words. So you have 8 such things. So one head, now let me call W1, W1, W1 here. How will my next, so how will these equations for my next head look like? What are the equations for next head now? Right, right. So let me use superscripts now. 1, 1, 1. Should I put this on x's? No. X's are very unique. Okay. So what will my second head do? Exact same thing. This will become Q2, this will become K2, V2, X's will remain the same. What will happen to these parameter matrices? They will of course change. The whole reason to do everything here is to learn a different set of parameters. Okay. So exact same equations but different parameters. If you have different parameters, do you have these vectors potentially different? This is all we are doing. Because x1, x's, they are fixed, they don't change. Okay. So you have how many such heads? 8. You have 8 such heads. So each block will give you a 64 dimensional, I have rotated it. Okay. So this will be 64 numbers coming from one head. Then you will have 64 coming from second. You will have 64 coming from the 8th one. So 64 cross 8 gives you 512. So that is my 512 now. Yes. You don't like number 8 or what? See, what was self-attention doing? Remember our earlier example. What was that? The animal didn't cross the street because it was too tired. So in this case, it refers to the animal. So this is one self-attention you want to capture through this. Can you think of another sentence in which, let's say, two pronouns? This is a very specific example again. Let's say there are two pronouns. So how can we change this sentence? The animal did not cross the street because it was too crowded. Now the same it refers to, it does not refer to animal anymore because it was too crowded. So what was crowded? The street. Okay. Now think of a situation in which you have two pronouns referring to two different subjects in the same sentence. Can this happen, or this is a big deal, this will never happen? This can happen. Okay. So one attention will not be able to take care of this relationship between two. It will take care of just one. You keep 8 heads thinking that 8 is a good number to capture all such kind of dependencies in a sentence in 512 tokens. Right? So there is nothing specific with this number 8. We'll see. When we'll come to GPT, we'll know that they don't keep 8, they keep 12. Okay. So 512 again, what will this guy do? Or maybe, but you can do it. This is 512 output, 512 input. Right. So how many parameters here? But I mean, multi-head attention, is that okay? Or just a second. So the time is over. Let me just give you the equations to compute multi-head, and the rest of the things we do in the next class. And you should be able to understand this because we have already done everything. So right now we are still at self-attention layer, and this is what you are computing. Tell me what is this calculation giving me, and we go. So forget this. This is something I am supposed to tell you. Rest everything you tell me. So this is a scalar because you are taking under root of something. So this is a scalar. Okay. So keeping this as a scalar, just explain me the rest. Sorry. What is this part doing? Forget decay. So we'll maybe bring this in the next class. So forget this one right now. Okay. So I'll just cross it. What happens to Q cross KT? What are the dimensions of Q? I'm short of letters. This Q is not same as that Q. That was WQ. Now this is Q. So what can this Q be? Guys, this one equation is representing everything that this self-attention is doing. What is self-attention doing? Q1 cross K1. It is also doing Q1 cross. So if this is my, let's say this is my Q1, this gets multiplied with a K1, right? And this actually gets multiplied with K2 and all the way until so this is a matrix. This is which matrix? K transpose. This is Q. What will be the next thing in Q? Q2 all the way until Q512. Okay. Now, what is this whole thing representing? Q1 dot K1 plus Q1 dot K2. These 512 dot products, you were computing this to calculate what? V1. So right now you have just taken dot product. What will be the output of this dot product? 11 बजे क्लास है क्या? कहाँ पे है? होगी? Okay. So what will be the output? So what is this guy supposed to be? So 512 cross 512 cross 64 maybe. Each Q1 is 64 and this guy must be so 64 because each K is 64. So this guy is 64 cross 512 and that should give me 512 cross 512. And does this make sense? Why 512 cross 512? Because see, there are 512 units here and for every unit you are taking how many dot products? 512. For every unit you are taking 512 dot products. So for total 512 units you are taking how many dot products? 512 cross 512. So this is the matrix of all these dot products that you are talking about. So this is Q1 dot K1 and so on. Let's continue this in the next class. Okay.